Imagine two particles, tiny, invisible to the human eye, separated by light years of space. One spins, the other responds instantly as if they're somehow still connected. No wires, no signals, just action, mirrored at unimaginable distances. This isn't science fiction, it's real. Welcome to quantum entanglement. Quantum entanglement is one of the most fascinating, mind-bending, and experimentally confirmed phenomena in all of physics. It challenges what we think we know about space, time, and even the very nature of reality. Albert Einstein famously called it spooky action at a distance, because for all his genius, even he found it deeply unsettling. So what exactly is quantum entanglement? Why does it matter? How does it work? And what could it mean for the future of technology, communication, and our understanding of the universe? Let's unravel the invisible thread that connects the cosmos. At its core, quantum entanglement is a phenomenon where two or more particles become linked in such a way that the state of one instantly determines the state of the other, no matter how far apart they are. If you measure one particle and find it spinning up, the other must be spinning down, or vice versa. But wait, how does one particle know what happens to the other? And how can it react faster than the speed of light? To understand this, we need to take a step into the strange world of quantum mechanics, where particles aren't just particles, they're waves. They exist in multiple states at once in what's called superposition. A particle doesn't have a definite position, spin, or energy until it's measured. Until that moment, it's a cloud of possibilities. Now imagine you have two such particles and you entangle them, usually through a process like splitting a photon in a special type of crystal. These two particles, although now separate, are no longer independent. They share a single quantum state. Measure one, and the other reacts instantly. Always? It's not that one particle is secretly pre-programmed to respond. That idea, called the hidden variables theory, has been tested, and it failed. Experiments have shown that no local explanation can account for what's happening. This isn't just weird, it's revolutionary. The origins of entanglement go back to a decades-long philosophical and scientific battle between two titans of physics, Albert Einstein and Niels Bohr. In the 1920s and 30s, Bohr was one of the main architects of quantum mechanics, embracing its weirdness and randomness. Einstein wasn't convinced. He believed in a universe that was deterministic, that things didn't just happen without a cause. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a famous paper, now known as the EPR paradox. They proposed a thought experiment showing that if quantum mechanics were correct, then it would allow for faster-than-light communication between entangled particles. That, they argued, was impossible. So, quantum mechanics must be incomplete. Bohr disagreed. He insisted that the act of measuring one particle doesn't send a signal to the other. It simply reveals a correlated outcome baked into the math of the universe. The argument continued, unresolved, until the 1960s. That's when physicist John Bell entered the scene. Bell developed a mathematical theorem, now called Bell's inequality, that could be tested in real experiments. If entangled particles followed hidden rules as Einstein hoped, their measurements would obey certain statistical limits. If not, those limits would be broken. And when the tests were finally run, starting in the 1970s and accelerating in the 1980s and beyond, the results were clear. Quantum mechanics wins. The universe really is that weird. Let's get practical. How do scientists actually create and test entanglement? One common method involves a crystal called beta barium borate BBO. When a laser beam passes through it, a single photon can split into two lower energy photons, each entangled with the other. These photons are then sent in opposite directions, sometimes through fiber optic cables, sometimes across open air. When a detector captures one photon and measures a property, like its polarization, the corresponding measurement on the second photon, sometimes kilometers away, shows an instant correlation. These experiments are repeated thousands, even millions of times. The results are statistically overwhelming. The particles behave like two halves of a single system, not two separate objects. Scientists have pushed this further. In 2017, Chinese researchers used a satellite called MICHUS to entangle photons and send them between Earth and orbit, breaking distance records. They proved entanglement survives even in space. That was a giant leap, not just for physics, but for secure global communication. Here's the catch. No, at least not yet. Entanglement is not a tool for faster-than-light messaging. While the outcomes are correlated, they're random when viewed individually. You can't control the outcome of the measurement, so you can't use it to send a message. You need a classical communication channel to compare results. That said, entanglement can be used to build ultra-secure communication systems. In quantum cryptography, entangled particles can detect if someone is eavesdropping on a transmission. Any attempt to intercept the entangled state disrupts it and reveals the intrusion. This makes entanglement a powerful weapon in the world of cybersecurity. Entanglement is also the secret sauce behind quantum computers. Traditional computers use bits, zeros and ones. Quantum computers use qubits, which can be both 0 and 1 at the same time thanks to superposition. But when qubits are entangled, their power explodes. It's like having all the possible solutions to a problem running in parallel, with the system narrowing down the correct one in record time. Google, IBM, and many other companies are racing to build quantum machines that could outperform today's best supercomputers. Already, quantum computers have shown they can solve certain problems that would take classical computers centuries. Imagine modeling molecules to discover new drugs, or simulating the behavior of atoms in a fusion reactor, or cracking encryption codes in seconds. Quantum computing, powered by entanglement, could change everything. Entanglement doesn't just revolutionize technology, it reshapes how we think about reality itself. If two particles can affect each other across light years, does that mean space isn't truly separate? Is the universe fundamentally non-local? Some physicists believe that space and time might emerge from deeper quantum connections, that what we see as reality is just the surface of a much stranger underlying truth. Others suggest that entanglement could even play a role in consciousness, though this idea remains controversial. Could your mind be entangled with other parts of the universe? Could thoughts and particles be linked in ways we don't yet understand? Philosophers, scientists, and dreamers are all asking the same question. If everything is connected, what does that make us? Of course, quantum entanglement has become a favorite trope in science fiction. Movies like Interstellar, Avengers, Endgame, and Tenet flirt with the idea of entangled time and space. Shows like Stranger Things and Dark use entanglement as a metaphor for deep, invisible links between worlds. While these stories often exaggerate the science, they reflect a real fascination with what entanglement suggests. That the universe is far more mysterious and interconnected than we imagined. And who knows? Today's science fiction is often tomorrow's science fact. Quantum entanglement is more than a scientific oddity. It's a window into a deeper order of reality. It shows us that separation is, in some ways, an illusion, that the smallest building blocks of the universe are in constant, silent conversation across space, time, and understanding. Einstein feared it. Bell proved it. Today, we harness it. And tomorrow, we may live in a world where quantum entanglement connects not just particles, but minds, machines, and maybe even entire worlds. In a universe bound by invisible threads, the greatest discovery might not be that everything is entangled. It might be that we always were. You made it all the way here, brain spinning, questioning if time is even real, and you're still not subscribed? Look, this channel isn't just content. It's a mental roller coaster through black holes, brain glitches, and bizarre theories your school never dared to teach. If you're into stuff that blows your mind and makes you say, wait, Lasti, what did I just watch? Then yeah, you belong here. Smash that subscribe button so we can decode the universe together. or at least get really confused trying. And hit the bell too, because if time is fake, notifications better be real. Let's get lost in the weirdest questions of existence, one rabbit hole at a time.